What is up, YouTube? This is Noah. Harmonics are a very interesting concept within music, as well as within physics. On an actual string instrument, we are able to guess and use our intuition in order to find these harmonic points. Here's what they sound like on an actual guitar. So open string is the first one, just there. And then the next one's about an octave up, half the length approximately. Sounds like that. The next one would be about right there. The next one is right there. Ooh, that's a good one. And so on. But yeah, there's quite a few of these on the guitar. You can tell by the way that was recorded that I have only the most professional of materials.
Recording materials.
Anyway, we are able to also derive these points mathematically. The equation that describes is as follows. F sub n equals n times f1, where n is a positive integer. This equation basically says that the frequency of the nth harmonic is equal to the product of n and the frequency times the frequency of the first harmonic. This still does not give us the position of where the harmonic is, though, relative to the length of the full string. Since wavelength, aka where to touch the guitar in order to find that harmonic, is the inverse of frequency, we take the reciprocal of the equation to see the distance away from the end of the guitar string we need to touch in order to hear the harmonic. This means that the second harmonic would be at half of the length of the string, third harmonic would be third of the length of the string, and so on, just like in this picture. Here's how we derive it using the information we have from an article on the inharmonicity of guitar strings by Murray et al. We start out with the wave equation, which is T with string tension times a second derivative of y with respect to x is equal to mu, which is like string mass per unit length, times the second derivative of y with respect to time, where y is height, x is a function of distance, and t is time. So y would be a function of distance in time, or position in time. Now, in order to solve this, we would use a differential equations approach. Note that this equation has a very similar form to the F equals ma equation, as you can see below. The m is like the mu, mass and all. A is the d squared y over dt squared term, or since y is like a position, the second derivative of that is acceleration, you may have learned. And then the left side is F, or force. In order to solve this, we guess the ansatz, or a solution, of the form you see below. Y of x and t equals a e to the power of I times omega t minus kx. Omega's angular velocity, k is a constant related to position changing with height. I is an imaginary number, and then a is just a constant related to amplitude. You have not learned how to do this, and you would learn in differential equations too if you choose to major in math. But for now, I will just give you guys a solution. So you can find these two equations using the ansatz on the original equation we were given. The top one is the wave height with respect to only time, and the bottom one is the wave height with respect to only position. Using the fact that f, or frequency, is 1 over lambda, which is wavelength, we can also find that lambda 1, or the wavelength of the first harmonic, full length of the guitar, would be L. We can plug this into frequency, or F1, that we found on the last slide in order to get the first harmonic frequency. It looks pretty good, huh? Well, not quite. This approach only applies to perfect strings that are unaffected by anything else in the world. That's how they would function. That is not what we have, and it's not quite possible in the real world. We must have a different equation for a real guitar string that accounts for a thing called the bending moment. Bending moment is a reaction induced in a structural element when an external force or moment is applied to the element, causing the element to bend. Here's what the bending moment looks like on an actual guitar. See how the guitar, when it's plucked, it wants to go back to its resting position? That's the bending moment force being applied. The new equation becomes the same as before, but then now there's a new term, minus ys I over m, fourth derivative of y with respect to x. It could almost make sense, but the fourth derivative seems a little bit confusing. There's a source on David Moore on Waves in Harvard Scholar that gives a better explanation of this. It is because the bending moment, or resistance to bending, is proportional to the curvature, which is the second derivative of the wave equation, and then the resulting net transverse force is proportional to the second derivative of the bending moment. The resulting harmonic frequencies from this are f sub n equals n times f naught times the square root of 1 plus bn squared, where n is a positive integer. Keep in mind f naught is still the frequency of the first harmonic, just looks a little bit different because of slightly different math, but physically it is the same as f1 in the other equation. Below is what the b constant is, and we have already stated all the constants included in it. The math is not quite as simple here and would result in quite different solutions that would just cause confusion if I went ahead and did the steps. So hopefully my voice has been soothing enough to be trustworthy. The math ends up working out if we assume that k is equal to n multiplied by pi divided by the length of the guitar. And then we end up finding out that the first frequency is V divided by 2L, or the length of the guitar. And V is, just like earlier, it is the square root of the tension divided by the mass per length of string. In order to find the exact position of these harmonics on an actual instrument, we must know all of its constants, as well as take the reciprocal of the equation in order to get wavelength rather than frequency. We can also do this intuitively using music knowledge, which is another talk for another time. Since we do not have the constants, I think we will stop here for now. Hopefully this was helpful. Please like and subscribe. Sources.